Hey everyone, in this video I'll be making my way through the practice exam 4. Okay, I think this is our last video. So let's get started. Number 1, this says evaluate the Riemann sum for this function x cubed minus 5x. It says taking sample points to be right endpoints. So that's crucial. And a equals 0, b equals 4, so we're going from 0 to 4 in other words, and then we have these 8 intervals, so n equals 8. So a couple formulas. We have, first of all, that delta x equals b minus a over n. So in this particular case, delta x would be 4 minus 0 over 8, in other words, 1/2. So this will be the size of the widths of the rectangles. Naturally, if you have 8, you're going from 0 to 4, right? So you need half units width. Then we need to figure out at what x location do we evaluate the function to get the rectangle's height, right? So for that we need x sub I, I'll write that here, x sub I. And for right endpoints, x sub I is a plus I times delta x. So in this case we'd have 0, since a is 0, plus I times 1/2, right? Same delta x that we just found a second ago. In other words, we would have 1/2 I. Okay. So for part 1, what we're going to do is want to evaluate the sum, the Riemann sum, right? That's what this thing was saying. So that formula will be I equals 1 to n f of x sub I times delta x. That's in general. So in particular here we have n as 8. We have x sub I as 1/2 I. And we have delta x as 1/2. So from there, our particular function is this one here. So I'm going to plug 1/2 I into this function here. So we'll have the sum from 1 to 8 of 1/2 I, and then I need to cube according to the function, minus 5 times 1/2 I. And I'll go ahead and then multiply by delta x, which is 1/2. Okay. So the 1/2 can actually come all the way out front, and then I'll do some simplifying here. So I'll just bring 1/2 all the way out front. Then we have the sum, right? The sum only cares about I, so since the 1/2 doesn't involve I can bring it all the way out front like that. I goes from 1 to 8. Then we would have, if I go ahead and cube, 1/8 I cubed. Then continuing, I would then have minus 5/2 I. And this is all in the sum. Okay, so I can split this into two sums. So maybe I'll use the summation properties this time. So we have 1/2 out front. I'll just keep that out front. And then I'll have the sum, I equals 1 to 8. And actually maybe I'll bring the 1/8 out front. So I'm bringing this 1/8 just out front of this new sum, and then leaving this I cubed, and then I'll have minus, I'll go ahead and do the same thing, 5 halves, and then the sum from 1 to 8 of just I. And all that is being multiplied by a half ultimately. Now for the actual formulas. So if you look on one of the pages in the notes, I forget which page it is right now, but you'll have a formula there for the sum on I cubed from I equals 1 to n. It just so happens that Rn is 8. So when it comes time to evaluate that formula, we'll just have n equals 8. So using those formulas on whatever page that is, I can replace. So I'll have still 1/2. Still I'll have this brace 1/8 times, and the formula for the sum on I cubed is n, so it'll be 8 times 8 plus 1, right? So that's n times n plus 1 squared. Well, I'll hold on to the square for now. It's all over 2, and then I'll square outside this way. So this is the replacement I'm making for the sum on I cubed. Let me just make that clear. So that's that replacement. The sum on I has its own replacement, and we're going up to n equals 8 again. So I'll have minus 5 halves, and then the formula for the sum over I is just n times n plus 1 over 2. So we'll have times 8 times 8 plus 1 over 2, and braces. So whatever number this is our answer for part 1 here, actually. So hopefully this helps. I'm kind of showing you guys how to use the sum formulas even to estimate, right? We're going to use the sum formulas down here to find the exact in a second, but you can use them here too. So simplifying this, okay, so I'll have 1/2. These braces, okay, 1/8 times, so this would be, I guess, 8 times 9, 72, 72 squared over 4. And then minus 72 over 2, 5 times 72 over 4. Let's see, I should have just grabbed a calculator. Okay, so if I did that right, let's see, I got 36. Cool. So here's my estimate, 36, and that would be, you know, some square units for area. So let's go ahead and see what the exact area is, right? This is part 2 now. Evaluate actually this definite integral by using the limit of the Riemann sum. So not just the sum that we just saw, but we're going to tack on that limit as n approaches infinity out front. Okay, so to redefine a couple things, delta x is 4 minus 0 over n. This time we're just going to leave it as n. X sub I would be 0. Again, a is still 0, plus I times delta x. I guess I didn't simplify. Delta x would just be 4 over n. So I times 4 over n. So in other words, we get just 4 over n I guess we can leave it that way. All right, and what we're going to do here, instead of just doing the sum, now we're going to tack out a limit out front, as then it goes to infinity. So we need to evaluate the limit n goes to infinity of the sum I goes from 1 to n of f of x sub I times delta x. All right. So I'll go ahead and start writing that, and this is our particular function still here. So we have the limit as n goes to infinity of the sum I goes from 1 to n of, well, I'll just write it in steps. We would have x sub I cubed minus 5 times x sub I. And then we would need to multiply by delta x. So this is the limit, and goes to infinity, of actually replacing that stuff now. So x sub I for us is this 4 over ni. So I'll have 4 over ni cubed minus 5 times 4 over ni, and then we don't want to forget about delta x, which is 4 over n. Okay, so something to keep in mind is that the sum, which is where we're starting, because we need to kind of start from the inside out, the sum is only really relevant with respect to I. We're going to n, but really the sum's kind of variable is I. So all these things involving I are going to have to obey that sum. Anything that does not explicitly depend on I, though, can come out in front of the sum, but it can't leave the limit until the n's get evaluated, and the n's actually need to go towards infinity. So 4 over n I can actually bring right here, but I can't bring it out front of the limit because it depends on n. So I'll go ahead and do some of that type of thing. After I do that, I'll go ahead and simplify also at the same time. So we would have the limit as n goes to infinity, and then I'll go ahead and bring out the 4 over n. I'm going to write some braces. I'll be able to have a 4 cubed, so I'm just doing some quick algebra. I'll have an n cubed out of this cubing here, and then that'll leave the sum going from I equals 1 to n of I cubed. Similar work over here, I can bring out a negative 20, and I'll also be splitting this up into 2 sums, okay? So 20 over n it looks like, right? Here's the 20 over n. This 4 over n is all the way out front right now. And then that'll just leave the sum going from 1 to n of I here, and then n braces. Okay, hopefully that went okay. Let's continue. So now that I have the sums kind of just defined with respect to I cubed and I, we can make those similar replacements, right, that we did up here, except instead of having 8s, I'm going to have n's. So going ahead and doing that now, we'll have the limit as n goes to infinity of 4 over n, braces, and then we'll have this 4 cubed still, n cubed, and then the formulas for I cubed is n times n plus 1 all over 2, but then all squared, minus Still have that 20 over n. And then the formula for the sum on I is n times n plus 1 all over 2. And then end those braces. Okay. A lot of details here. Okay, simplifying a bit. Let's see, so 4 over n times 4 cubed over n cubed times n squared. Going ahead and just squaring things. This is now over 4 minus. So I'm kind of passing this limit across this difference now. Okay, we can cancel some stuff. So the 4's, the one of the n's, looks like anything else. Over here, not much going on, I guess, but you could cancel these n's. You could say that 2 goes into the 20 10 times. And then you could do some factoring, actually. So we can say the limit goes from n to infinity of 64. You can factor out n cubed plus 2n squared plus n. And then this would be over, what's left there is n cubed minus the limit, n goes to infinity of 80. I guess that would be 40. Just make sure I get this right. 40 n squared plus 40 n all over n squared. Okay. So then we go ahead and evaluate the limits. So we would get let's see, ultimately 64 minus 40, which would equal, I'm just running out of room, I guess 24 square units. Ooh, sorry about that. So that would be our exact value. You can check that. All right, let's just do a quick check. So integrating from 0 to 4, this function cool. Okay. No more of those. So I'm going to go next to number 4, actually, the practice exam. That took enough time. So evaluate the integral by interpreting it in terms of areas. Okay, so I guess I'm technically supposed to do this in terms of areas. So yeah, you could do a couple different things. This integral would be equivalent to these two integrals. If you wanted to kind of think of this as these two different areas, we would have a 1 here if you want, then you could. So this area, let's just draw a picture for it. you would have something like a line coming through this way from 0 to 10, right? So you'd have a triangle. For this one, you would have, well, I guess if you just want to think of it as positive 1, you would have this 1 going from 0 to 10, and you would have that area. So you would have these two different areas to add up, or I guess subtract. So if I look at this one, we'd have a triangle with base 10. So maybe I'll bring this over here now. So I'll call this area 1 and area 2. So area 1 would be a triangle. So we have 1/2 the base, which is 10, times the height, which would be 10 evaluated within this function, right? So the height would be 3/2 times 10. Okay? So what would that be? Go ahead and type this in. Times 5 times 10. So 75, it looks like, if I did that right. So this would be 75 squared units. And then for the second area, the one up here, this rectangle, it's a length 10 rectangle, and then it'd be a height 1. So we'd have 10 square units there. And then taking this one minus this one, we'd have 75 square units minus 10 square units, so 65 square units. Let's do part 2. So more kind of geometry and interpreting these things in terms of areas. You could split this up again into two different integrals. So we could say from -2 to 2 of just this linear piece, and then we could subtract -2 to 2, the square root of 4 minus x squared dx. So the pictures going on here, we would have this line going from -2 to 2 with slope 3. So we would have these two triangles. Something to point out, this would be positive area, this would be negative area. So they're actually going to cancel out. This is going to produce 0. Anyways, let's look at this one. This would be a circle centered at 0, 0, but just the upper half of that circle, right? Since it's just the plus case. I'm not thinking about the minus, I'm just thinking about the plus that's right here. So we would have essentially from -2 to 2, if you think of kind of rework this, this is a circle centered at 0, 0, but just the upper half. So we would ultimately want to find this area and then subtract again this other area. Just by symmetry, this is going to be a 0 right here. So this is going to be 0 minus, and then half a circle of radius 2. So we'd have pi times 2 squared, but then over 2, since it's half, just the upper half. So -2 pi square units would be the result of that integral, and you could check it. So integrating with one of these calculators, you could type this in. 3x minus the square root of 4 minus x squared, and then from this -2 to 2. Sometimes takes them a minute. Or 2 minutes. Or 3 minutes. All right, we'll just move this to the side while it's thinking, and I'll move on. Hopefully it'll pop up. Let's go on to number 5. So there's its estimation, by the way. So and our answer was -2 pi. You can see that's a good answer. It wouldn't have given us the exact answer though, which is something to note, right? Here's the exact, and we got that in terms of areas. And if you just relied on your calculator, you would just get this number, and maybe you wouldn't know that it's exactly this, right? -2 times pi. It's that number that we were looking at. On to number 5. So it says use part 1 of the fundamental theorem of calculus to find the derivative of each function. So g prime of x will be the square root of 1 plus x squared. Okay. Part 3. So something we can do, we actually want this variable limit to be the upper. So this would be the same as the negative of 0 to x squared, the square root of 1 plus cosine t dt. So I can go ahead and differentiate now, and I'll need the chain rule. So f prime of x equals negative the square root of 1 plus cosine of x squared, but then times d dx of x squared. So we get f prime of x, and the end is -2x, I'll just bring it out front, times the square root of 1 plus cosine of x squared. Moving on to number 6. It says evaluate each integral, leave each answer in exact simplified form. So now we're just going ahead and integrating. We don't need the limit of the Riemann sum or anything like that. So finding the antiderivative of this integrand here. So we'd have 1/4 x to the 4th plus x cubed minus 4x, evaluating from 1 to 4. So we would have now evaluating at 4, 1/4 of 4 to the 4th plus 4 cubed minus 4 times 4. And then minus parentheses so that we subtract the entirety of this. 1/4 of 1 to the 4th plus 1 cubed minus 4 times 1. I believe we're going to get 459 over 4, which is equal to 114.75, either way. Go down to part 4. So I can split up this integrand. So 2 to 5, I'll say 1 over x plus x squared over x dx. So simplifying, and then finding the antiderivative. So ln of absolute value of x plus 1/2 x squared, and then evaluating from 2 to 5. Okay, so if you'll spare me a little bit of the arithmetic just to cut down on the length of this video, ultimately ln 5/2 plus 21 halves. All right, on to number 9. This one says an oil storage tank ruptures at t = 0, and oil leaks from the tank at this rate. And this is in liters per minute. So it says how much oil leaks out during the first hour. So important to note that this is liters per minute, and we're being asked to find the amount in the hour. So what we want to do is integrate for sure. So we're going to integrate r of t with respect to time. And since that rate is with respect to minutes, to look at the first hour, we need to go from 0 to 60. Okay, so we'll integrate from 0 to 60, 100 e to the negative 0.01 t dt. Okay, we can bring out that 100. I'll just start by doing that simple step. What I'll use is a U-Substitution. So I'll let U equal negative 0.01 t. That way du equals negative 0.01 dt. So I don't have the negative 0.01, so I'll need to offset. So what I'll do is divide by negative 0.01, both sides. Okay. What you'll find if you divide 1 by negative 0.01 is you'll get negative 100 du equals dt. All right, so that'll be my substitution for dt. So in other words, this new integral with respect to u will look like e to the u, and then times negative 100 du. And what we've been able to do is, if we want to just stick with the original limits of integration, we can do that. We would just integrate and then go back to t's, or we could switch these. So if I plug the lower limit into my substitution here, I get, well, when t is 0, I still get my lower limit is 0. If I plug in the upper limit, so negative 0.01 times 60, the new upper limit is negative 3/5. Okay. So now I can integrate. So maybe I'll bring out the negative 100 first, actually. So negative 100 squared from 0 to negative 3/5 e to the u du. So this would be equal to negative 100 squared times e to the u, and then evaluated from 0 to negative 3/5. So we would get negative 100 squared times e to the negative 3/5 minus e to the 0. And then rewriting the negative 100 squared, we can write negative 10,000 times 1 over e to the 3/5 minus 1. And then maybe I'll leave it over here in the end as 10,000. So just switching and actually distributing minus 10,000 over e to the 3/5 power, and this is liters. Okay, it's something like 4,000 liters. if you type that in. All right, moving on. Here's number 10. So it says integrate each of the following. This is a series of U-Substitution examples. So I have this negative x cubed plus 3 inside of the sine function. I have a 2x squared outside. So what I'll do is I'll let u equal negative x cubed plus 3. Then du is negative 3x squared dx. Okay. I have a 2, so maybe I'll pull that 2 out. All right, so this would be a 2, and then integrating x squared sine, I guess, negative x cubed plus 3 dx. So I have an x squared, so what I'll need to do is divide by this negative 3. So I'll need to offset this. So negative 1/3 du will come in for x squared dx. All right, so this will be my substitution. So we have 2, and then this integral sine of u times negative 1/3 du. Okay, so I can bring that negative 1/3 out front, so negative 2/3, and then the integral of sine u du. This would be negative cosine, and then that negative cosine times the negative 2/3 would be positive 2/3 cosine of u, but u is negative x cubed plus 3, so I'll just write negative x cubed plus 3. This is an indefinite integral, so I'll add on c. Okay. Moving on, let's try a definite integral. So number 11. So here we have sine t over cosine to the 4th. So what I'm going to do actually is let u equal cosine t. And then that way du equals negative sine t dt. And I have a sign there. I don't have the negative, so I'll divide by negative 1. So negative du will replace sine t dt. Okay, so I have now 1 over u to the 4th. Instead of cosine to the 4th, I have u to the 4th. I have sine t up here, so I need to offset that by bringing in negative. So this is times negative du. So in other words, negative out front, and then u to the negative 4 du. And this is going from 0 to pi over 4, but I can go ahead and change those limits. So if you plug in 0 for t, so cosine of 0 is 1. So my new lower limit is 1. Plug in a pi over 4 into cosine here. So that's like 45 degrees, right? So that'll be root 2 over 2. Okay. And now we can go ahead and integrate. So I'll raise this power by 1 and divide by that new power. So this is u to the negative 3 divided by negative 3 from 1 to root 2 over 2. So this would be positive 1/3 times 1 over u cubed. So 1/3. So now just plugging in these limits. And ultimately, you can simplify that down to 2 root 2 minus 1 over 3. You can check me on that, but okay, let's move on. So number 12. So this one says the rate of growth of a fish population was modeled by this equation, where T is measured in years, G in kilograms per year. If the biomass was 25,000 kilograms in the year 2000, how much more biomass is predicted for the year 2020? Okay. So if this is the rate, if we integrate over the time, then we'll be left with just the biomass. So what we want to do is integrate from 0 to 20 years, this given function, 60,000 e raised to the negative 0.6t over 1 plus 5 e to the negative 0.6t squared dt. So what I'll do is make a substitution. So I'll let u equal 1 plus 5 e to the negative 0.6t. And that way du, so go ahead and you can imagine the chain rule taking effect. The derivative of 1 is 0. So eventually we'll get 5 times negative 0.6 e raised to the negative 0.6t dt. And going ahead and isolating what we have. So what we have is this. So I need to divide by this stuff here. After dividing, that's the same as negative 1/3 du equals e to the negative 0.6t dt. So this is what will come in up top here. You can also plug in the 0 and the 20, right? So you can plug in the 0 here. You get a new lower limit, right? So plug in 0 here, you get a 6. So we'll have 6 now. Plug in the upper limit. So plug in the 20 now for t, and you'll get your new upper limit with respect to u. So that would be 1 plus 5 times e raised to the negative 12, I believe. Let me see about that. And then we'll have, maybe I'll write the 60,000 out front. And then 1 over u squared times negative 1/3 du. So you can simplify that down to negative 20,000 if you bring out the negative 1/3. 6 to 1 plus 5 e to the negative 12 u to the negative 2 du. So negative 20,000 times, so raise this power by 1, divide by the new power, and then evaluate the 6 to the 1 plus. Okay, after you plug that in, you'll get something like 20,000 times plus 5e to the negative 12 minus 1/6. And that's about equal to, so I'll leave it there. And that's a number of kilograms. And this is about equal to 16,666.05 kilogram. And this would be more. All right. Let's look at number 13. Find the area of the region bounded above by y equals e to the x. Bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. Leave your answer in exact simplified form. So just a quick picture. E to the x, something like this. Y equals x, something like this. X equals 1, x equals 0. This would be this region. And we're just looking for the area between this region. So that area formula will be, from the beginning to the end of your interval. And then whatever the upper function is, so this is the upper function of x minus the lower function of x. I'll just say it like that. We had different notation before, but that's what I mean by upper and lower. So in this case, the area will be from 0 to 1, e to the x minus x dx. Since e to the x here is the upper function throughout this interval that we care about, it's going to be the upper, and x will be L of x. Integrating, we get e to the x minus 1/2 x squared from 0 to 1. Evaluating, we get e to the 1 minus 1/2 times 1 squared minus e to the 0 minus, I guess we'd get a 0 there. So all we get is e minus 3/2 in the end. That would be the amount of area. On to number 16. It says find the area enclosed by these lines, y equals x minus 1 and the parabola y squared equals 2x plus 6. Leave your answer in exact simplified form. So just to draw another quick picture, we kind of have this sideways parabola happening. And then we have this line also happening. So this must have an x-intercept down here of -3. And then it looks like just imagining solving for x equals 0. About 2.5 there, and -2.5 down here. And then this line, y equals x minus 1, is going to be coming through right about like this. So we have this area here. Okay, so it looks like we're going to want a couple integrals. I'm trying to think of how I want to do this. I guess we need everything in terms of y. So I'm going to write this one as y plus 1 equals x. And then I'll write this one as y squared minus 6 over 2 equals x. Right? And with respect to x's, this one is now going to be my upper, basically. Right, so we're going to have like the area equaling y limits, so c to d of some upper function of y minus some lower function of y dy. So this will be my upper for this case. Okay, since we're going with respect to y, I have to figure out these limits, right? So what we need to do is set these things equal to each other. So we need to figure out basically where x minus 1 squared equals 2x plus 6, right? So if I basically use the substitution method, solving that, just to save us a little bit of time, the y lower limit will be -2. The y upper will be 4, okay? You're going to get solutions that come out of this as x equals 5 and x equals -1. Then you're going to plug those in to these and figure out what your y values are. So we are going to integrate from -2 to 4 the upper function, which is y plus 1, minus this lower function, which is the parabola, y squared minus 6 over 2 dy. So simplifying a bit, we can write -2 to 4, -1/2 y squared plus y plus 4 dy. And now finding the antiderivative, -1/6, that'll turn into y cubed plus 1/2 raised to the power by 1, all that good stuff, plus 4y, evaluate from -2 to 4. So after all that, you'll get an 18. Moving on, here's number 17. Okay, so it says if the birth rate of a population is this people per year and the death rate is this people per year, find the area between the curves from 0 to 10. What does this area represent? Round your answer to the nearest person. Okay. So just to draw a quick picture, we'd have a couple exponential models, basically, doing slightly different things, where this is the birth rate and this is the death rate. The area between those, if you just kind of conceive what that would be, is roughly the number of people added to the population, right? The difference between the birth and the death. And this is roughly because there are other factors. There's immigration, right? So there are other factors that add to populations rather than just people dying and being born. But this is roughly that amount of people being added to the population. So if we integrate from 0 to 10, this 2200 e to the 0.024t model, and then we subtract by this death rate model, we are finding this area between there. Right? So I'll split that up into two integrals just to make things a little better. I'll bring the constants out front as well. Oops, missed a 0. Right? So further integrating, we're going to need a couple of substitutions. So I'll go ahead and write those out. So for this one, I'll let 0.024t be represented by u. I don't know why I wrote it in that order. So in other words, u equals 0.024t. So du equals 0.024 dt. So I'll need to divide by this amount. So I'll have that 1 over 0.024 du replaces dt. For the other one, I'll let u equal 0.018t. du would then be 0.018 dt. And then dividing again in a similar way, we get 1 over 0.018 du equals dt. So those things will come in, and we can make substitutions out for our limits as well. So 2200 and then e to the u times 1 over 0.024 du minus 1460 e to the u times 1 over 0.018 du. I think I got all that right. I didn't write the limits, so you do need to figure out where 0 and 10 map to. So for this one, you're going to get different limits, right? So you're plugging in 0 into this t here to get this new lower limit. So that's still 0. Plug in a 10 up here, you'll get 0.24 as your new upper limit. Right now I'm plugging 0 and 10 into this substitution to define what the new limits are for this piece. So plug in a 0, we still have a 0. Plug in a 10, we get 0.18, right? So 2200 over 0.024 times e to the u from 0 to 0.24 minus 1460 over 0.018 times e to the u from 0 to 0.18. Okay, so now actually going ahead and plugging in things, we'd have 2200 over 0.024 times e to the 0.24 minus e to the 0 minus 1460 over 0.018. Right? And this is about, I'll say about 8868, and this is people. And so this would be, is roughly the number of people added to the population. During this time. Okay, so we were supposed to interpret it. On to number 18. So it says, for the following exercises, draw the region bounded by the curves, then find the volume when the region is rotated around the x-axis. Okay, so we have x to the fourth, x equals 1 and y equals 0. So just to draw the x to the fourth, so if I evaluate at 0.5, I get something around 0.1. If I evaluate at 1, I get something around 1. So I'd have roughly this curve. and then the x equals 1, and then the y equals 0 defines this area here. If I want to find the volume when this thing gets rotated around this axis, well, kind of a hypothetical chunk of this area is literally attached right to the axis of rotation, right? So this would be the disk method. Okay, so the volume would be, well, we're just going from 0 to 1. This thing is pointing at the x direction, so everything's with respect to x. So we have pi times the function value squared dx, and we're going from 0 to 1. Right? So this would generate this disk. Its area would be pi r squared. The radius is variable, right? Our radius of this disk is variable with respect to the function, right? Multiplying by the thickness of the disk then generates a volume. So we'd have pi from 0 to 1, x to the 8th dx, right? Actually finding the antiderivative, we now have pi over 9, x to the 9th from 0 to 1. The 0 is not going to produce anything because the antiderivative is a factor of x. So just plugging in the 1, we get pi over 9. This would be cubic units if we wanted to include units. Moving on to some other one, I guess. Maybe 20. All right. Okay, it says for the following exercises, draw the region bounded by the curves, then find the volume when the region is rotated around the x-axis. Leave your answers in exact simplified form. All right, so we have this parabola, or at least a piece of it. So we have a y-intercept of 6, right? Looking at this one. And then it's opening downward. So I guess we would have this as its vertex. Then we have this constant function going right through 2. If you plug in a 2 for y, then you'll get plus and minus 2 for x. So it must be that this parabola intersects right there. So this is a rough sketch of the picture. So this is the area that is implied. And we're rotating this around the x-axis. So for a hypothetical chunk of this area, it is still pointing at x, so we'll integrate with respect to x for sure, but there's this gap, right? There'd be this kind of donut shape. So this is washers. So to find that area, what I can do is actually double. So since this is symmetric, I'll just go from 0 to 2. So the volume will be double going from -2 to 2. So I'll just go from 0 to 2. Pi times the outer function squared, which is 6 minus x squared, minus the inner function squared, which is just the function 2, and then I have dx. So I need to integrate this thing, and that'll define the volume of this region when rotated around this x-axis. So simplifying a bit, I can write 2 pi, integral from 0 to 2, 36 minus 12x squared plus x to the fourth minus 4 times dx. Maybe just rearranging a bit. 2 pi x to the fourth minus 12x squared. And then 36 minus 4, I can just write 32 dx, and then we'll go from 0 to 2. So antiderivative, I have 1/5 x to the 5th minus 4x cubed plus 32x, then going from 0 to 2. So 2 pi 1/5. I'll just write it all out this time. So actually performing the part 2 of the fundamental theorem. Zero is not going to produce anything, but I'll just write it out. So in the end, I believe what we're going to find for this volume is 384 for 5 pi, and that would be cubic units. I'm going on to 21 actually. Okay. So it says, use the method of cylindrical shells to find the volume of the solid obtained by rotating the region bounded by y equals root x and y equals x squared about the y-axis. Make a sketch of the situation. So x squared, just to sketch that out, would do something kind of like this. So it grows this way, and then the root x kind of grows in the opposite way. So I'll just roughly draw it like that. So this is the x squared, this is the root x. Down here, once they cross, just to be clear, this is the root x, this is the x squared. So this is this region, and we're going to go ahead and rotate this around the y-axis, it was said. So this hypothetical chunk of area, if I'm using the shells, will be pointed at the x-axis. That way the shell gets created as I rotate. So I'll need to go from 0 to 1. So the volume will be the integral from 0 to 1, 2 pi times x. Right, since it's being rotated around the y-axis, the radius of this thing is just x at any location. We're not like separated from the axis of rotation, so we don't need to offset x or the radius at all. But these heights are variable with respect to these two limiting functions. So what I'll do is I'll figure out the height of this generated shell by taking the upper minus the lower. So the upper will be root x, the lower will be x squared. Then we'll have dx. So this is the height of this. This is the radius of this. And I'm kind of imagining this shell being generated. So it would have a radius of x, and it'd have a height of the difference between these two functions. So 2 pi, 0 to 1. I'll go ahead and multiply x through, so this would be x to the 3/2 minus x cubed dx. Antiderivative, we'd have 2 pi I'm raising 3 halves by 1, so I get 5 halves, and then I divide by 5 halves. Divide by 5 halves means multiply by 2/5. So in the end, you're going to get 3/10 pi, I believe, for the volume. So 22, I believe this is the last one I'm going to do. Okay. So it says, let y be this, calculate the arc length of the graph of y over this interval 1 to 3, round the answer to 3 decimal places. So our arc length formula is you're integrating from a to b, in this case it'll be from 1 to 3, the square root of 1 plus the derivative of the function squared dx. Right, and in this case it'll be y prime squared. So I need to find y prime. So doing that first, I'll differentiate this function. So I'll have x squared, and then I guess I'm thinking of this as 1/3 x cubed plus 1/4 x to the negative 1 for the derivative purposes. So I'll multiply down and then reduce this by 1. Right? So this is y prime. I have x squared minus 1/4 over x squared. If I combine these fractions through a common denominator, that might help. I'd ultimately get 4x to the 4th minus 1 over 4x squared. And then I need to square that, unfortunately. So now doing all of this squared, just preemptively, right? Because we're going to need to square it anyways, so I'm doing that work separate. So we have 4x to the 4th minus 1 squared over 16x to the 4th. So that'll come in for this. So we have the arc length as the integral from 1 to 3, the square root of 1 plus 4x to the 4th minus 1 squared over 16x to the 4th, and then dx. Okay, so the goal now, or a goal, can be to get these fractions together. So to do that, I'll get a common denominator. So 16x to the 4th over 16x to the 4th, I can think of that as 1. So actually combining now, I can write the square root of 16x to the 4th plus 4x to the 4th minus 1 squared all over 16x to the 4th dx. And I could split this up, the quotient rule for radicals. So I'll go ahead and take the square root of this piece. So 1 to 3, and I basically have the square root of this upper stuff. And that upper stuff, if you expand that, you can write 16x to the 4th plus 16x to the 8th. So I'm foiling this out. Minus x to the 4th plus 1. And that's all over now the square root of 16x to the 4th. Then we still have dx. And you can combine these, you can simplify this to 4x squared. So 1 to 3. We have that just 4x squared now, instead of this thing. I can write the square root of 16x to the 8th plus 8x to the 4th plus 1 dx. 1 to 3. So just rewriting. This actually factors as a perfect square. So I can rewrite that as the square root of 4x to the 4th plus 1 squared. This is the limit. This is not a cube root. This is a square root. This goes all the way under. This is now dx. And now actually canceling this square root and that square, we have 4x to the 4th, 4x to the 4th plus 1 dx. Sorry, this should have been a 2. So this should be squared. This should be squared. So I'll continue down here, simplifying a bit more. 1 to 3. I can write x squared, right? Just splitting this up, plus 1/4 x to the negative 2, also just splitting that up, dx, antiderivative finally, so 1/3 x cubed minus 1/4x, and then going from 1 to 3, what I ultimately got after that arithmetic was 53/6. And that's arc length, so that would just be like linear units if you wanted to include that. All right, good luck on your exam, you guys.